Okay, welcome Goa campus and Hyderabad campus. I can see only 4 people, 5 people there. 6th one is coming, 7th is coming. So here we have only 3 Jani campus, not anybody more. They won't be coming. They won't be coming. No, you don't know. Fine, anyway we will start. Okay, so we have a test tomorrow, 5 o'clock. No, not 5 o'clock, 11 o'clock. At 11. So let us start. Whatever I will be covering today will not be a part of your curriculum. So curriculum is what I have already listed on the Nalanda. So now here we are going to look at, we are looking at op-amp topologies. And here we are looking at high gain in one stage. So high gain in one stage may be a simple differential amplifier. It can be a simple differential amplifier. It can be a very simple differential pair. This is maybe output differential, fully differential or single-ended output. Accordingly, you have to define your, or you have to change your topology. So within one stage, if you want to go for more gain, I need to cascode. I need to use the principles of cascode. If you go for cascode, so 2 PMOSes in the upper section, 2 NMOSes in the lower section. Okay, so this is cascoding, use of cascoding. This is V in plus, V in minus, this is ISS. Okay, so this is VB1, VB2 and VB3. Similarly, VB1, VB2 and VB3. And this may be my output. Okay, if you want to do single-ended means I would be removing this connection. And I would be going for current mirror kind of a current mirror load. I have to convert it into a current mirror load. Okay. Similarly here, this section will become a cascode current mirror load. So I need to make it a cascode. And here you would have 2 NMOSes. This is ISS. So this would be single-ended output. If you go in for cascode. Okay. Now this takes 1 VGS and 1 VGS, 2 VGS. So this point needs at least VDD minus 2 VGS headroom. And if VGS is 1 volt, you are losing 2 volts. One problem is this. Same thing is here. If I replace this with a cascode current mirror, I would be losing on the headroom. This is IREF, grounded. So minimum I require over here is, if you remember, this will come to VGS. So this is VGS. This is also VGS. So this comes to 2 VGS with respect to ground. This is 1 VGS down. This comes to VGS. And this is V overdrive. The minimum I require here is VGS plus 1 V overdrive. So again, this is a very big headroom, because if VGS is 1 volt and V overdrive is 0.2, so I am losing. So it is 0.9, VT is 0.7. So I am losing roughly how much? 1.1 volt. So 1.1 volt I am losing here, and here I am losing 0.9, I am using 1.8 volt. So if this is 3, I do not have enough margin for the swing. Okay? This node will be limited in swing. I am losing. So I need to go in for something which is consuming low voltage, and yet it will give you high impedance. Because I want a high RSS here. I want a very high RSS here. So how to implement a high RSS current mirror? High RSS current mirror with 2 stacks, with 2 stacked transistors. Yet low voltage headroom. Low voltage requirement. Yet it has a low voltage requirement. Clear? Mansa?
Yes, ma'am.
Kirti, Mansa, Akash?
Yes, ma'am.
So, we are looking at the implementation of a low voltage high RSS current mirror, okay, which has a low voltage requirement. So, I cannot go in for cascode or Wilson. So, if I look at my cascode and Wilson connections, okay, they both give you high ROut. I hope you all have read about them. Okay, so we have a cascode and I have a Wilson. Cascode means, if this is, I am drawing NMOS configuration. Okay. This is cascode. And here you may connect your differential amplifier or any other amplifier. The minimum you require is VGS to VGS. This is also VGS, so this comes to VGS. So this comes to VGS plus V overdrive. Minimum you require this much. If I look at Wilson is again two-step resistors. Here you come apply potential pair. So what is the minimum requirement here? The way we draw it is like this, if you remember. Okay? This is how we draw Wilson. Sorry, I think I make a mistake. This comes here. This is a Wilson. What is the minimum requirement? This is VGS. This is VGS. So this is also VGS matching. This is also VGS. So VGS and this is 1V overdrive. Minimum requirement. Minimum requirement. But this will come to VGS. VGS, this will come to 2 VGS. With respect to ground, this is 1 VGS down, this comes to VGS. And again, if this is 1 V overdrive, minimum you require here is VGS plus V overdrive. It's the same thing in Wilson and RSS here is, we all know, it's a 2 stacking here. It is roughly equal to GM, RO plus RO plus RO. That's the minimum. I know these values using cascoding principles. Same thing I get in Wilson also. Wilson is, there is a feedback. So R out without feedback, without. So if I remove this transistor, okay, so just look at this pair. There is a cascoding with a source degeneration of 1 by G. I can write the expression as GM RO into 1 by GM plus RO plus 1 by GM. Same expression, but RO replaced by 1 by GM. Because transistor is diode connected. Now we have a feedback. Look here. There is a feedback from here to here to here to here. This is a feedback. There is a feedback happening. From this point, any change here will cause a change here, which will come here, negative will come here, negative here, so this will go here. There is a feedback going on. Feedback through this transistor. I use the principles of feedback. Which type of feedback is there? If I short my output, this is my output node. Current at this node is still available. It is not off. It does not vanish. It is a current feedback. Current. So you are getting a current output. It's a current sample. When you short your output, current is present. Okay? It's a current output is sampled. So according to current, this is 1 by GM. It drops across 1 by GM, gives you a voltage. This voltage goes as input to this transistor, produces a negative. It acts as a common source amplifier, produces a negative output over here. This acts like a common source amplifier. So whatever output is present here, whatever perturbation you get here, it goes as input. This produces a gain times input with a negative value. This negative value comes here because this VGS has to be constant because it is constituting a constant current IREF. So when you change here, because VGS has to remain constant, it goes up, this also goes up. If this goes down, this also goes down by the same amount. So as if the effect is propagates from this node to this node. Simply. And then it goes to the back gate of this transistor. If this is negative, this will negative, VGS will decrease, current will decrease. So any initial increment will make the current to, it will set a negative feedback and cause the gate to reduce. As a result, the current will roll back. So R out with feedback now will be initial R out because of current sampling 1 plus A beta. A is, look at this transistor. Look at this transistor very carefully. It is, you are feeding your input here, getting your output here. Your effect is coming here. Okay? So as if you are moving from here to here. So it is a common drain application. Gate is, what is the gain of this? Now roughly because of 1 by GM, gain would be R. Because gain of common drain amplifier is GM into the RS by 1 plus GM RS. RS here is 1 by G. So A is this. Beta is feedback factor. That comes from this feedback network. It comes from this feedback network. And what is the gain? Gain from here to here? Gain from input to output? It is a gain of CS. So beta is minus, suppose the gain is A. So gain is how much? What is the gain for CSA? Minus GM R. This is diode connection. It would be 1 by GM plus R. IREF, assume it's giving you high impedance. Infinity or very high value. So very high value means GM RO parallel. This will be roughly minus GM R. So I have A and beta both with me. A is, remember, it is negative is coming because this is mod value. So I get an R out of X as initial value. So this is RO, this is RO, 2 RO. Okay? 2 RO into 1 plus A beta. So 1 plus A is, what is A? Half. A is half common drain amplifier gain. Beta is GM RO. I am not taking negative sign because negative sign has been taken care of in the negative feedback correction. So I get R out with feedback as roughly 2 RO into GM RO by 2 cancels out, roughly GM RO square. Same as this. So roughly Wilson and Cascode gives you same performance. Wilson and Cascode give you nearly the same performance. Yes, sir?
Yes, ma'am.
If any query you have, Goa campus, kindly ask. So we are looking at implementation of high RSS current mirrors. Yes?
Ma'am, can you explain calculation of beta once again? Like,
What
for
is
that
beta? Beta is the feedback factor. Okay, so you have to look at the feedback network. Feedback network starts from this point. It goes this way. From this way, comes here.
Yeah.
So look, you have to find the gain. So if I say this is V1 and this is V2, you have to find beta is nothing but V1 by
B2.
V2. What is V1? If I say that this is behaving like a common source amplifier, because any perturbation here comes here, goes as input to this transistor, produces the output here. It is a common source amplifier configuration. Okay?
Ma'am, So,
Yes.
so for the load, won't we consider the above MOS? Like,
You consider what is the upper situation. Look here. It is IREF. And here you have a diode connected MOS. Clear? This is your situation. This is common source amplifier. This is V1, this is V2. Okay, what is the load? Tell me.
infinite, like.
No, this can be very high. It is
Yeah.
going to be a reference circuit.
High. Yes.
So look from this point, what is the R in? R. Common gate connection.
Okay.
Okay, it would be RL plus RO by 1 plus GMRO. Even not even, rather it is not even common gate because this is diode connection.
Diode connected, yeah.
So this is simply 1 by GM plus very high value.
Yeah, ma'am, I got it now. Thank you.
Fine?
Yes, ma'am, fine.
So we see that Cascode and Wilson, they give us the same performance. Okay? So we get roughly the same RSS and we receive roughly the same voltage headroom. So if I want to have a even higher RSS and even low voltage headroom, what should I do? So here we have a low voltage cascode connection. Low voltage cascode. That is, cascode is modified. So rather, I again have a look at, this is amplifier connection here, a cascode. This is a cascode. In a normal situation, I make in the reference arm both transistor diode connected. Remember, I normally go for this connection. But here we make a change. Because I do not want this to be VGS plus V overdrive. Initial value for a cascode, which comes out to be for VGS to be 0.9, V overdrive to be 0.2. This gives me a loss of 1.1 volt. It gives me a loss of 1.1 volt, which I don't want. So I want minimum, I say this is to be saturation, this is to be saturation. So 1 overdrive here, 1 overdrive here. I can easily bring both of them in saturation only by using 2V overdrive. That means a total voltage loss of only 0.4. So why should I go for 1.1? So I do a back calculations. For this to be V overdrive, this comes at VGS minus VT. This is VGS and this is VGS because they are matched. So this comes to 2 VGS minus V or VGS plus V overdrive. Clear? Akash? Is there any Akash at Goa?
Yes, ma'am.
Yes. Clear? How am I doing the calculations? So this comes to, this node will automatically come to 2 VGS minus VT by with respect to ground. Now this has to be VGS. Now remember, now I am not making this connection. So how to generate this bias for this? I need to generate. Okay? So this has to be VGS, remember. And this also has to be VGS. I am assuming all 4 transistors matched. So now this is 2 VGS minus VT. And minimum I require here for this lower transistor M1 to be in saturation is 1 V overdrive. So it is VGS minus VT. Because 2 VGS minus VT here, 1 VGS down, this will automatically comes to VGS minus VT. So here we make a connection. So now to connect this, I'm making a connection now which we did last time also, low voltage cascode connection. And I generate this potential 2 VGS minus VT separately. This is generated through an extra reference arm. I generate this extra reference. Okay? I generate it. And here you put a resistor. This is VD. This is IREF. Let me redraw. Let me redraw this part. Okay? So we have IREF. Low voltage cascode connection. And this is to be how much? 2 VGS minus. Now I need to generate this potential. So what I do? So this is going to be VGS. Okay, so I can put this. So this comes to VGS. This is VGS. So this comes to 2 VGS. This comes to 2 VGS. Diode connection VGS plus 1 VGS, 2 VGS. I need a potential 2 VGS minus VT. So what I do is that I take it up, have a resistor here, and then this is IREF. And I configure the value of R such that for the given I through this arm, the difference is, the potential drop is 1 VT. So that means this node automatically comes to 2 VGS minus VT. Clear, Srinivas?
Ma'am.
Apurva? Divya? But then I have to add extra circuitry because this is to be generated. This is a drawback. You are consuming more power. Because total power is now going to be VDD here, and VDD will be coming here also. So total DC power consumption will be VDD into 3I. So I am consuming more power. But I am reducing the voltage headroom requirement. Now I can generate a high RSS current mirror only by using 0.4 volts headroom. Only by using 0.4 volts. Okay? Now I use the principle of gain boosting. Suppose I need to further increase. Now I have become very greedy. Okay, low voltage I have received, I have got at the expense of more power consumption and more extra circuits. But can I increase my RSS even further? I can increase. I look at my Wilson RSS expression. What is happening here? So I do, it is giving me a RSS equal to GM RO square. Can I increase it further? I know I can increase it further. Remember Wilson? R can be made to increase as 1 plus A beta times. R can become R times 1 plus A beta if you use negative feedback. So I use negative feedback. So what I do, very simple. I again put a common source amplifier here and feed it here. Okay, it's a common source amplifier. How will you make this now? Redraw. I am redrawing this part. Look very carefully. I am redrawing it. This is amplifier connected here. Okay. So this is coming from here. This part I will not show. So this is coming from there. Okay. This part is your Vx. So Vx is this. I am not drawing the second. I hope you understand. You can correlate the two graphs, the two figures. Now my aim is to show you this configuration. Gain boosting, because whatever is RSS, I want to make it RSS times 1 plus A beta. I want to make it RSS times 1 plus A beta. So I will make a common source amplifier. It's a common source amplifier. Using the concept from Wilson. I am using the concept from Wilson. So if this is any change delta happens, this goes to minus A times delta. This gate voltage comes down So delta increases, this decreases, so this decreases, VGS decreases. Initial increment in current is reduced. So current remains more or less stabilized. Why? Because there is no change in current. Current is rolling back. If you increase, suppose some increment in current happens, because of negative feedback action, the current rolls back. The gate voltage comes down, so current rolls back. Okay? So your Q point is more or less stable. I bias does not, or ISS changes very, very little or negligibly, or it doesn't change at all. So I am able to stabilize my current source. That is, RSS going to be very, very high. That is what I mean by RSS to be high. Change in the current is very less. R is VSS by ISS. If ISS is not changing or changing very little, RSS will be very large. Clear? So, but there is a problem now. This cannot come to, remember, we have brought it to 1 V overdrive. But now, because this is connection, I cannot have it less than 1 VT. So this cannot be brought to VGS minus VT. You cannot make it operate at 2.2 volts. Otherwise, this MOS common source amplifier will not operate. So I have a drawback. So I modify my feedback. Now let's see how am I modifying. I am redrawing it here. See very carefully and then we will stop. I am drawing it here. Very carefully you look at what I am doing. This is what we have. Amplifier connected here. This is grounded. Okay. What I am doing is that this load is coming, it was going to the gate. I will not make it go to the gate, rather I create a structure like this. You will say, madam, it is not a common source amplifier. Yes, it is not a common source amplifier. If this is an IREF, maybe some other IREF 2 or 3, whatever IREF I have here, okay, any delta increment here will cause this node to increase, because VGS over here has to be constant, so this will also goes to the same increment. So delta will come here. It will propagate to this node. So I am able to bring the delta perturbation over here. I am able to bring the delta change at this node. Okay. Now I create a common source amplifier here. Now I create a common source amplifier here. Maybe IRF 2 or 3, whatever it may be. Now I create this is my common source amplifier to which a delta input is going. And you are getting a delta minus A times delta output which I feed here. I am getting a feedback. And now my output RSS will be RSS times 1 plus AB. How much was RSS? How much was RSS? GMRO square. So what is the new value for this? Calculate the new value. What is 1 plus A beta? Use the initial previous value. What we were taking as 1 plus A beta? Remember, A was half, beta was GMRO. So what is the new RSS you are getting? Yes, Kirti?
I got confused. I didn't understand the delta V part that is fed to the...
Okay. Any other who has understood, who wants to answer this question? Yes, Akash?
Ma'am, I am doing, ma'am.
You are doing. Nisar, Srinivas?
Is it GMRO square into 1 plus GMRO by 2?
Yes, very good. Who's that?
Manasa.
Manasa. Correct. Very, very correct. So roughly you are getting an RSS of GM cube, GM square, RO cube. Now the bell has gone. I hope many of you have not understood the concept. I will repeat it. Don't worry, I will repeat this concept. Okay? Meanwhile, you have a test tomorrow. If you find time, just give it a reading. Otherwise, this is not a part of your test. Don't worry. Okay, we'll repeat this last part. The bell is good. Huh? Yes or no? What's the time? 10:34 only. Sure? Oh, then why am I leaving? I think, okay, very sorry. Let me continue. Maybe, yes. Very correct. I thought it was. Okay, let me repeat. I'm very sorry for that. So let us repeat what. Let us repeat what I did. Remember cascode. I'm using gain boosting. So I look at my last arm. So this is my cascode. Here you connect your differential amplifier or any other amplifier. I want a V overdrive and a V overdrive here. Okay, so that this comes to only 2 V overdrive. This is I am creating from a low voltage cascode connection. This I am getting from a low voltage cascode connection. Okay, this is 2 VGS minus VT. Now I'm going to use I have to get the what? We have to get the gain boosting done. Gain boosting. So I am now using the principle of gain boosting. So I am creating a common source amplifier. Common source amplifier, how do I create? I create a common source amplifier here. Clear? A common source amplifier. Now remember, what is ISS? My RSS is given as, suppose this is VSS, a VP, the VP by ISS. If I want RSS to be high, change in ISS has to be nil. That means due to some reason, if current is increasing, there should be some action happen in the circuitry such that the current rolls back. So that this delta change is very, very small. Then only RSS will go very high. Currently my RSS is roughly GM RO square. I want to increase it further. So I am using the concept of gain boosting. So what I do is that I create a common. Now you will say, madam, you connect these 2 points together. But the moment you connect these two together, whatever VGS you have, you cannot bring this node to V overdrive. It has to be VGS. Because it cannot operate at 1 V overdrive. And if I make this hard connection, I would limit my, it will never come to 2 V overdrive. Clear? Answer?
Yes, ma'am.
Any query from here? Anybody whose name I don't know? At Goa campus? Anybody whose name I don't know?
Ma'am, Salahuddin.
Salahuddin, yes. Salahuddin, so do you understand this concept?
Yeah, ma'am.
So I cannot make this connection, this dash connection I cannot make. So, but still I want a gain boosting, I have to find a way out. How to do gain boosting? So I use the concept of propagating the voltage. So if due to some reason, say, maybe because of, say temperature change, VT decreases, current increases. ISS increases. As a result, ISS is flowing across RS, so this node voltage increases. So this node voltage will also increase. Let me say this increment in node voltage is delta. Increment in node voltage is delta. Because of this, now current is increasing. Now I want to bring the current back. So I have to have a reverse action. That means current should roll back. So current can roll back only when VGS decreases. So I have to decrease my VGS. Which VGS? This VGS I need to decrease such that the current sensor will go back, so that these are in series. The current through this will also go down. Clear? Clear, Kirti?
Yes, ma'am.
So I have to somehow give a negative voltage here. The negative voltage will come if I have a minus A times delta here. With delta input, I get a minus A times delta here. Okay? So minus A times delta. How to this delta I need to bring it here. I cannot make a direct connection. So I have to make an indirect connection. Again, I get a concept from Wilson where we have a propagation of the voltage. I make a diode connected MOSFET here and I connect this. So this is now delta, and this I make it to have a constant current flow, maybe IREF3. These IREFs can be different. This is a IREF. I can create multiple current mirror arms and change my W-band ratios to tap multiple IREFs. Okay? So, I have an IREF3 because IREF3 suppose is 20 microampere. For a W-band say of 10 value or 20 value, this will have a specific VGS. I don't know whatever it may be, but because it has to carry a current of 20 microampere and W-band is fixed, the VGS has to remain fixed. The VGS has to remain fixed. As a result, if this node is increasing by delta amount, if VGS has to remain fixed, this node will also go up by delta amount, so that the difference of the two nodes remains the VGS. Is this clear? Again, you can say no if you don't understand. Yes, Vasanta? And from Goa campus?
Yes, ma'am.
So I am able to now, because of this connection, I am able to bring this delta over here, though they are not directly connected. They are not directly connected. And because of this delta coming up here, this node will come to minus A times delta, which I fed to the gate. So gate voltage is reducing. As a result, I get a RSS as initial RSS 1 plus AB time. This would be initial value GM RO square 1 plus A is a gain, common drain amplifier gain, that is half, beta is GM RO. So this roughly gives you GM RO, GM square RO cube by 2. RSS has become very high and I am getting a very low voltage implementation, that is voltage requirement is only 2V overdrive. Clear? Or you have still a doubt?
Excuse me, ma'am.
Yes.
Ma'am, from the low voltage cascade connection,
Yes.
we are pulling out a line which has 2 VGS minus VT.
Yes, so this is incomplete. But I think we completed it when I showed you. Okay, you want me to complete it here? I will complete. Let me complete it here. So this is still incomplete, you are saying. So
Yes.
we did it last time. Not last time, just some 10 minutes back I did it. So this was a low voltage cascode. Okay? Clear? All you need to do is either you take the arm like this, put an R and IREF. This we did just from 10 minutes back.
Ma'am, this was
Either
my
you do
question,
it.
ma'am.
Huh?
This is not, ma'am. I'm asking whether the connection will go any further right-hand side.
No. Because 2 VGS minus VT here will come from this node. This node is a full circuitry from VDD to ground. Okay? It is not required. A 2 V overdrive means this can come to, this should come to VGS plus 1 V overdrive. And this node can come, it can settle at that point because minimum it requires only 1 V overdrive. So it can come to VGS plus 1 V overdrive. This node can settle to that value. There is nothing which says you cannot come to this value. So this node can come to 2 V overdrive easily. Yes, for this circuitry I need to generate this potential, which I can do either by using this, or you can make a similar circuit for this also. You can make a similar circuit for this also. You can make. How? I can make it like this. This you cut down. So I am making it for here. Okay. So this has to be VGS plus V1 V overdrive. I can make the same circuit as I have here. How? It can be a current mirror, a common source amplifier, a diode connection, and this is exactly same circuit as I have here. I can bring it here. This is not there. Okay, so this node will be VGS. This node comes to VGS minus VT. This is VGS, and this will be the difference. The difference will be how much? This is VGS minus VT. VGS minus VT. What is this difference? Will be 1 VT. Will it be in saturation? Yes. Yes, minimum you require is 1 V overdrive, which is 0.2. VT is 0.7. All transistors will operate in saturation region. Yes, any query? Any query that you have?
Ma'am, you have given us two solutions.
Yes.
Which one should be used when? During implementation?
So, clear, very good. So here, this node is coming to 1 V overdrive. This is your biasing arm, which is connected to amplifier. Clear? So, if this is 1 V overdrive, and remember, ISS by IREF, I would be looking at this ratio, current mirror. This must be 1, if I am assuming matching, proper matching. Or, if I write, this must be. Now, remember, it would be dependent on 1 plus lambda VDS parameter. If everything else is same, these parameters can be different because of the VDS difference. What is the VDS here? It is V overdrive. Possible VDS is V overdrive. Now look here, if I go for this solution, what is the VDS here? It is VGS, they will be different. So as far as possible, this is 1 V overdrive, this is 1 V overdrive. I should try to even have this also as 1V over drive. If this is not giving me, I would rather go for this solution. Because this enables me to have 1V over drive. As far as possible, the reference arm and the bias arm, they should have the same parameters. So that when you transfer, when you mirror, there should be no degradation of the current, even because of lambda effect. If I go for this solution, I can have this node at 1V over drive. If I go for this solution, possibly, I may not. This may influence the circuitry. This may. Otherwise, if there is no solution, go for this. So as far as possible, we try for matching between the two arms. Because designing this reference arm will be different from designing this reference arm. Look, because there is a different configuration here. So I tried making the same circuitry here. As far as possible, the reference arm and the biasing arm, they should have matching in the circuit configuration also. So that the two behaves complementary to each other. But nobody says that you cannot use it. You can use it, but then be ready for deviations. Be ready for it. Clear? Yes, any other query? Fine, so tomorrow you have a test, let us not go any further. If you have any query, you can ask. For tomorrow's test. If I am not specifying any constraint and you are allowed to make choices, then you can. But then just one thing, whatever you choose or whatever you take any values which are not given in the question paper, then please justify. Please justify your assumptions, why you are assuming a particular value, why you are approximating, justify. That is very necessary. Why you assume that this will approximate, this expression can be approximated, or you are using a particular value which is not there in the question paper. Okay, you should justify your answers or your assumptions. That is very necessary, so that I can check accordingly. My solution can go accordingly. If there is any problem, please ask. Do not assume that, okay, everything would be right. Sometimes there may be problems. There may be, though we try hard not to have any problems in the question paper. We try to make them flawless. But even then, if you have any confusion, you please ask. Kindly ask. Ask your instructor, he can contact me and we can resolve the problem. Okay? So do not just keep mum, please ask. Any other query? And bring your own paper, pencils, okay, calculators and all those things. Do not borrow that, because that takes a lot of time. That destroys time for yourself as well as for the other person also. Yes? So you should learn about small signal modeling, analysis, calculation of parameters, small signal parameters, GM, RO, R1, R in, R out, the gain, the high frequency intuitive explanations, high frequency behavior, parasitic capacitances, the different configurations that you have been taught, amplifiers, differential pair, cascode, folded cascode, common gate, common drain, differential pair, characteristics. Okay, all these things you should at least have a practice. Yes, Goa campus. Current mirrors are not. I haven't taught you current mirrors. Current mirror is this, whatever I am showing you. Today's part is not a curriculum. That is current. Today's is based on current mirrors. Okay. But the normal basic current mirror you can do, na? Cascode Wilson that you have been taught in, you were taught in your first degree course, bachelor's. Those things you can tackle. Advanced current mirrors that I have taught you, that may not be necessary. Huh? Yes, any other query for tomorrow's test? Fine then, I disperse the class. If you still have a query, you may either send me an email or just call me or ask your instructor to contact me. Fine? Yes.